Welcome to the Unit 9, Section 2 video on key features of quadratics from a graph. Recall that a quadratic function is a function that can be described as an equation of the form y equals ax squared plus bx plus c, where a cannot equal 0. And the reason a cannot equal 0 is because if a were 0, that x squared term would go away, and we're left with bx plus c, which would be linear. The highest exponent of a quadratic equation is 2. The graph of a quadratic function takes the shape of a parabola. So let's take a look at some of the key features. First, we have the axis of symmetry. It is the line that passes through the graph in such a way that each side is a mirror reflection of the other. Then we have x-intercepts, which also are known as zeros or roots. And they are the points or point where the graph crosses the x-axis. The y-intercept is the point where the graph crosses the y-axis. And finally, the vertex is the highest or lowest point on your graph. If the graph is pointed upward, then you're going to have a low point. If it's pointing downward, then you're going to have a high point. As previously shown, some parabolas open upward and some open downward. Notice that the only difference between the two equations is the value of a. When a quadratic function is written in the form y equals ax squared plus bx plus c, the value of a determines the direction that a parabola opens. If a parabola opens upward, the vertex is the lowest point. If a parabola opens downward, the vertex is the highest point. And so we refer to these two orientations as concave up and concave down. The value of a is positive when you're concave up. So your leading coefficient should be positive in a concave up graph, and it should be negative in a concave down graph. The parabola opens upward when it's concave up and downward when it's concave down. I think that's fairly self-explanatory. The vertex value, or y value, is a minimum when you're concave up because we have a bottom of the graph, and a maximum when it's concave down because we have the top of a graph. Let's go over some of the other features of quadratics, starting with many of the features that we've already seen earlier in this course. The domain of a function is the set of all possible x values. Unless a specific domain is given, you may assume that the domain of a quadratic function is all real numbers, notated by the interval negative infinity to positive infinity. The range of a function is the set of all possible y values. The range will be determined by the maximum or minimum. Remember that the range is the only interval feature that uses y values. End behavior describes what is happening to the function as x approaches positive and negative infinity. For this graph, we have as x approaches infinity, so we're looking at the right-hand side, f of x goes to infinity because the graph is pointing up. As x goes to negative infinity, looking at the left-hand side, f of x goes to infinity because, again, the graph is pointing upward. In fact, in end behavior for quadratics, you're either going to have both f of x's going to infinity or negative infinity, depending on if it's concave up or concave down. An increasing interval is a set of x values when the function is going up. A decreasing interval is a set of x values when the function is going down. So in this graph, I drew a dotted line along the y-axis, which is where the axis of symmetry is. We're decreasing on the left side, so negative infinity to 0, and increasing on the right side, which is 0 to infinity. A positive interval is a set of x values with corresponding positive y values. A negative interval is the set of x values with corresponding negative y values. In other words, positive intervals are where the graph is above the x-axis. Negative intervals are where the graph is below the x-axis. So here I have divided the graph into 3 sections. In the first section, it is positive from negative infinity to negative 2. Then we go below the x-axis and we are negative from negative 2 to positive 2. And then finally, we're positive again, going from 2 to infinity. Since there are 2 positive intervals, you need to union the 2 intervals together using the union symbol and the two intervals going from left to right. Let's determine the key features of this graph parabola. So the direction, since it's pointing upward, is concave up. Our vertex is located at the point 1, -4. The axis of symmetry is along the line x equals 1. We do have a minimum at y equals -4. Now, make these two connections. The x value of the vertex is your axis of symmetry. The value of your max or min is the y value in your vertex. The y-intercept is located at 0, -3. Our zeros, or x-intercepts, are located at -1, 0 and 3, 0. So there are two of them. Our domain goes from -infinity to +infinity. Our range goes from -4 to infinity, including the -4 because the vertex is a point on the graph. We are increasing from 1 to infinity. We are decreasing from -infinity to 1. Notice that we increase on one side of the axis of symmetry and decrease on the other side of the axis of symmetry. Our positive interval is from -infinity to -1, union with 3 to infinity. Notice that those two values are also our x-intercepts, and our negative intervals from -1 to 3. Finally, in behavior, since both sides of the parabola are pointing upwards, both ends are going to infinity. In this graph, we are concave down. Our vertex is located at 2, 1. Our axis of symmetry is at x equals 2. You can read the vertex for that. Since it's concave down, we have a maximum, and that maximum is at y equals 1. Our y-intercept is at 0, -3. We have two zeros, one at 1, 0, and the other at 3, 0. Our domain is -infinity to +infinity. That's not going to change. Our range goes from -infinity up to the y value of 1. We are increasing from -infinity to 2, and then decreasing from 2 to infinity. We are positive from 1 to 3, and negative everywhere else. -infinity to 1, union with 3 to infinity. And since this is concave down, both sides are pointing downward, and so f of x is going to -infinity in both directions. A rate of change is a ratio that compares the amount of change along the y-axis and the amount of change along the x-axis. So our average rate of change is y2 minus y1 over x2 minus x1, our change in y over our change in x. Now this may sound familiar, and it's because we've done this already, but we've done it for linear functions, and in linear functions, your average rate of change is called slope. This formula is used whenever the average rate of change is determined using an equation, table, or graph. So let's take a look at average rate of change from an equation. First, you're going to substitute the first x value into the equation to get y. Then you're going to substitute the second x value to get y. This will give you 2 points that you can use in the average rate of change formula. So let's try it out. We have f of x equals 2x squared plus 5, and we're going to go along the interval of 1 to 3. So this interval tells us our x values that we're going to be using. So we're going to plug in 1 into this function and evaluate it to get 7. So our first point is going to be 1, 7. Then we're going to plug in 3 and evaluate it to get 23. So x1, y1 is 1, 7. x2, y2 is 3, 23. It doesn't really matter which one is x1, y1 and which one's x2, y2. You just got to make sure that the x's and the y's go together. Then we're going to use our average rate of change formula, plug in all of that information, simplify the top and simplify the bottom, and then divide to get 8. For the next one, again, you're going to plug in your first x value to get the y value that goes with it. You're going to plug in your second x value to get the y value that goes with it, and that gives us our 2 points. Then we take our 2 points, plug them into the average rate of change formula, and do our subtraction on the top, do our subtraction on the bottom, and then finally divide to get 3. Average rate of change from a graph, you're first going to find the first x value on the x-axis and follow the vertical line until you reach the graph. This will be your first point. Find the second x value on the x-axis and follow the vertical line until you meet the graph. This will be your second point. Plug both points into your average rate of change formula and simplify. So let's find the average rate of change for each of these functions. From 1 to 4, we are first going to follow 1, x equals 1, down to the graph, and that point is 1, negative 6. Then we're going to go to 4, follow that up to the y value of 3. Put it in our average rate of change formula, and we get that the average rate of change is 3. For b, we're going over the interval of 3 to 6. So we follow 3 up to the point 3, 1. We follow 6 down to the point 6, negative 2. We plug in our x1, y1, x2, y2, and simplify to get negative 1. Finally, the easiest of all is to find the average rate of change from a table. Find the first x value in the table and the corresponding y value. Find the second x value and corresponding y, and then plug them into your average rate of change. So for this table, over the interval of 1 to 3, you're going to find that when x is 1, y is 5. When x is 3, y is negative 3. Just read it straight from the table. Plug in those values, and you get negative 4. For the next example, our x is negative 3, our y is 23. When x is 0, y is 8. Plug in your x1, y1, and your x2, y2 into the average rate of change formula, and simplify to get negative 5. Thanks for checking out my video in the Algebra 1 Honor Series. You can subscribe to my channel. I've got the next video queued up for you, and if you need to check out any of the videos in the course, I've got the course playlist for you here as well. Thanks for watching.